When we look out at distant galaxies, we see that they are all racing away from us. We see that the universe is expanding. The Big Bang Theory suggests that once the entire universe was compacted into an infinitely small speck at the beginning of time. But was this really the case? What parts of this theory are still under serious question? In the last episode, I showed you why the Big Bang Theory is right, or at least what parts of it pretty much definitely happened. Direct and convincing evidence tells us that the universe was once much smaller, hotter, and denser than it is now. We're actually pretty sure we know what happened all the way down to approximately 10 to the power of minus 32 of a single second after the hypothetical beginning of time. And at that point, the entire observable universe was around the size of a grain of sand. Now, we got down to that size by rewinding the laws of physics, and in particular running the math of Einstein's general theory of relativity backwards. But how much further can we rewind until we run into trouble? Well, things get pretty weird before that 10 to the minus 32 seconds. Now remember, when the universe was younger than 400,000 years, it was too hot for atoms to exist. Well, before 10 to the minus 32 seconds, it was too hot for the fundamental forces of nature, as we know them, to exist. In a previous episode, we talked about how the Higgs field gives particles mass. Well, at temperatures above 10 to the 15, or a quadrillion Kelvin, it stops doing that. Turns out that when you take this Higgs mass away from the particles that carry the weak nuclear force, they become just like the photon, which itself carries the electromagnetic force. This means that the weak and electromagnetic forces sort of merge into the one electro-weak force. For a very brief period, soon after the beginning of time, these forces are combined. It's called the electro-weak era. Sounds weird, but perhaps weirder is that it's not really a mystery at all. We pretty much know this happened because we can actually make bits of the universe do this. We can create energies needed to produce the electroweak state in the Large Hadron Collider. Yep, we can simulate the instant just after the Big Bang. Our theories look really good to that point. But once you get to a crazy 10 to the power of 29 Kelvin at an age of around 10 to the minus 38 seconds, it's expected that this electroweak force and the strong nuclear force, that's the force that holds atomic nuclei together, also become unified into one force. There are a lot of ideas of how this might happen, and we call these grand unified theories. Except they aren't theories in the same sense as relativity or evolution, because we don't know which, if any, are actually correct. The problem here is that we can't test them yet. We'd need to produce energies 1 trillion times larger than is possible with the Large Hadron Collider. Nothing we could build on the surface of the Earth could do this. And perhaps that's for the best. So, this is still a huge unknown. We do think that we can describe gravity and the shape of space-time at these densities and temperatures, but we can't confidently describe the stuff that the universe contained, the weird state of matter that far back. Okay, rewind a bit further to 10 to the power of minus 42 seconds of age and pack all of the galaxies in the entire observable universe into a space 10 to the power of minus 20th of the width of a proton. That's the Planck length, and here physics kind of goes out the window. See, at this point, general relativity comes into serious conflict with quantum mechanics, and we need a theory of quantum gravity, a so-called theory of everything, to go further. We can talk about why these theories don't play nice together and what some of the resolutions might be, string theory, another time. We're leaving it alone today because we don't actually know whether the universe was really ever this small. Remember, we've been rewinding the universe using basic general relativity. Is that valid? Well, we don't yet have direct evidence from those very early stages. But there are some clues still visible at later times, and those clues tell us we've missed something huge. Let's undo our rewind a bit. Fast forward, again to 400,000 years after that crazy first fraction of a second. The universe is space-sized, but it's still 1,000 times smaller than the modern universe. It's full of this hot glowing hydrogen plasma, but at 400,000 years, it's cooled down just enough to form the very first atoms, and in the process, release the cosmic background radiation. We now see this light as an almost perfectly smooth microwave buzz across the entire sky. That smoothness tells us that all of the material in the universe, when the CMB was released, was almost exactly the same temperature, around 3000 Kelvin, varying from one patch to the next by at most 1 part in 100,000 across the entire observable universe. Why is this so weird? If you have a cup of coffee and drop in some cold milk, it'll all smooth out and become the same temperature after a bit of time. Well, the universe works in the same way. But based on the simplistic expansion you predict from general relativity, when the CMB was released, there just hadn't been enough time for this mixing to have occurred. See, in order for the most distant patch of the universe we can see in that direction to have the same temperature and density as the most distant patch in that direction, there needs to have been enough time for something to travel between those points, to diffuse and even out that heat. And there just wasn't. Not even for light, the fastest thing that there is. Let's take this grain of sand-sized universe at 10 to the minus 32 seconds. A photon emitted on one side of that grain wouldn't have time to get to the other side, not even in 400,000 years. See, although light is fast, those opposite edges of the universe were travelling apart even faster. Another way to say this is that those edges of the universe have always been beyond each other's particle horizons. A quick refresher, here's a nice review episode on cosmic horizons. So, those edges shouldn't be in each other's observable universes. Not then, not now. This serious issue is called the horizon problem, and it's a big deal that we need to sort out. The only way around this problem is to somehow have the universe, once upon a time, be small enough so it could easily get all nicely mixed together, and then, pow, blow it up in size, much faster than general relativity would normally allow. The theory that describes this pow is called inflation. The idea is the universe started subatomic, small enough that it was able to even out its temperature, and then entered a state of insane, exponentially accelerating expansion, in which it increased in size by a factor of at least 10 to the power of 26, so 100 trillion, to something like our grain of sand size, at which point it slowed down to its regular expansion rate, but its edges are thrown way out of causal connection. Yet they look the same because they were once causally connected. This whole idea fixes our horizon problem. In fact, inflation solves a number of vexing problems with the Big Bang Theory. So well, in fact, that most cosmologists accept that something like this must have happened, even though we don't have any direct evidence for it. There are a number of explanations for how inflation might have happened, and some of them actually call into question our understanding of that very first instant of the Big Bang. In this sense, it may be more accurate to think of the Big Bang Theory not as a theory of the origin of the universe, but instead as a theory describing the period of expansion from a subatomic to a cosmic size. Aspects of this theory have such hard evidence that we know that the basic picture is right. However, as with every really well-established theory, there are boundaries to what the Big Bang Theory currently explains. Those boundaries are being chipped away at all the time. Perhaps the theory will eventually encompass a true origin for this universe. Or perhaps that question will take us far beyond the Big Bang. One thing I stand by: we can science anything, the origin of everything included. We'll get back to that on future episodes of Spacetime. In the last episode, we laid out the evidence for why the Big Bang definitely happened. You guys let us know what you thought. Electromechacat 3 asks why, if the universe is expanding, doesn't matter also get stretched with that expansion? Okay, this is a genuinely tricky question. It's not surprising that matter would not be stretched by expansion, because the bonds between and within atoms are vastly stronger than any degree of expansion on the scale of any material object in the universe. That's if it were even valid to extrapolate that expansion to the scale of objects, or even to galaxies. What we call the Hubble expansion of the universe arises from the Friedmann-Lemaitre-Robertson-Walker metric, which describes a space-time in which all matter is perfectly smoothly distributed. That works on the largest scales, in which galaxies and galaxy clusters are a speckled foam on top of a much vaster space-time. It doesn't work in galaxies or solar systems. For example, the solar system is better described with the Schwarzschild metric, dominated by the sun's gravitational field. In that metric, space is most certainly not expanding. So you can have regions of non-expanding space embedded in a globally expanding universe. Kalakashi asks, does this mean if you were to take every proton, neutron and electron in the universe, you could fit them all into a space the size of a grain of sand? This would be correct if you add the word observable before the word universe. Everything that we can see to our cosmic horizon, so the observable universe, was once compacted into something smaller than a grain of sand, and indeed much, much smaller than that. However, this isn't the same as saying that everything that exists was compacted into that volume. If our universe is infinite, then you can compact it as much as you like, and it'll still be infinite. We don't know how large the greater universe is, so we restrict ourselves to talking about the size of the observable part of it. James Beach writes, "In the beginning there was nothing, which exploded." Now, a lot of non-scientists like to repeat this statement, but no credible scientist has ever said this, nor believes it. So it's unfortunate that this statement is used to deride the Big Bang Theory. The Big Bang describes a series of events that happen to the universe following its existence in an extremely hot, dense state. We have a ton of evidence that the universe was once in such a state. Perhaps our understanding of this state will eventually lead to a theory of the origin of the universe. But the Big Bang Theory as it stands does not claim to explain such an origin.